Welcome to episode 21 of the exercise application assignment. Let's talk about what I did. So, we have wide grip lat pull downs, as usual, single arm neutral grip machine rows, upper back machine rows, easy bar French press, single arm cable tricep push down, lat prayers, and barbell shrugs. I did not remove barbell shrugs. Ooh, the camera's I did not remove barbell shrugs as I kind of thought I would. It just feels too good right now. I'm progressing with it really well, but it's definitely gonna have to come out soon, even though I'm enjoying it. But you know, I generally try to mess with things as little as possible because I'm kind of a perfectionist and really just want to keep messing with stuff over and over again, even when it's not beneficial to. So let's talk about how this applies to what we're learning. Talk about acid base balance quite a bit. Let's look at let's just run through a lot of the stuff. Let's try and connect some things here. So yeah, let's do our best to connect something. Where should I start? I've already kind of went over this, but this is something I kind of struggle with, so I'm just going to go over it again. So when hydrogen and HCO3-, which is bicarbonate, are diffused in the red blood cell, hydrogen lowers the pH and denatures hemoglobin, causing O2 release into the plasma, go to the muscle cells to help maintain the Krebs/ETC in mitochondria. But when bicarbonate leaves the red blood cell and binds to hydrogen in the plasma, which is from the NHE and the MCT, a small amount goes to the MBC. But then the HCO3 becomes H2CO3 and travels to the plasma. What's that? That's a buffer. It's taking hydrogen. Hydrogen goes down, pH comes up. We're raising our blood pH. But how? The heart pumps the blood. Why? To facilitate the expulsion of CO2 and wastes and delivery of O2 to the tissues. How? The blood returning through the vena cava pours into the right atrium, which allows 70% to fall into the right ventricle. Then it contracts, ejecting the rest. Then the right ventricle contracts, sending blood through the pulmonary arteries into the lungs to the capillaries, where adjacent alveoli containing O2 allow for the diffusion of O2 in, and HB offloading of CO2. Okay. Now, had a thought there. Yeah, so when we're talking about the PQRST, right, we have our atrial depolarization at the P wave, then we have our ventricular depolarization QRS complex, and our atrial repolarization in there as well, but it's hidden by that. And then we have the T wave, which is our ventricular repolarization, right? Pretty simple stuff. We can also use the terms systole and diastole there, but it doesn't exactly line up. I feel like in lecture it was mentioned depolarization is the start of contraction, right? It's where contraction starts. It's not where it's happening. So when we say systole, that's kind of like when it actually, you know, depolarization is like about to, right? That's when we're getting the signal because it's propagated down these intercalated discs, you know. But how? By carbonic acid makes it to the lungs, it becomes CO2 plus H2O, then it's expelled, changed for O2. How? Contraction of the diaphragm causes the lungs to expand, create a pressure lower than atmospheric. I think I talked about this last time. What is it? During heavy exercise, CO2 buildup is more rapid and pH lowers. Emphasis on exhaling, hyperventilating, will lower pH buildup. The blood returns to the lungs via the pulmonary veins and into the left atrium, which sends the blood to the left ventricle, which is stronger. Why is it stronger? Because it has to overcome greater pressures, more peripheral resistance. We have more branching, right? If you think about it, the route from the heart to the lungs is pretty short. There's less capillaries. There's less capillaries in your lungs than there is in the rest of your body, I think. I mean, the surface area of your lungs is as big as a tennis court. But if we think about it, there's probably less pressure. It's probably not as dense as the rest of the stuff in your body. At the very least, the rest of the stuff in your body appears bigger. You know, it appears like there's a lot more surface area there. But yeah, you know, peripheral resistance is the main thing we're going to be altering. Blood viscosity and blood volume should not change that much. So the way we're altering our blood pressure and stroke volume and vascular shunting a lot of times is through selective vasodilation and vasoconstriction.